I think we have a philosophy that we should always not feel comfortable where we are.
So we are, together with the artists, the creators. We are making the things and inventing the things that do not exist.
I think what we're doing is also part of this grand transformation of the energy for the future human societies.
So we always look for something in the horizon. And when we feel comfortable with what we're doing, it's time to change.
I think a key motivator for a lot of us at CPES is sustainability.
And that thing that we always feel that whatever we're doing, we're not doing for the population of Mars, but we are doing it for the other humans around, and we know it's going to find its way there. That's something that makes me real proud.
Together with the most innovative and creative industrial companies and partners, we are really working on the most toughest problems.
Because every day you solve a problem, even if it's a small problem, you feel very happy. Because I guess we just love playing circuits. You know, we blow up something, and second day you fix it. It's kind of a nerd thing, but it's excited. I think that is the very unique reason why I'm working every day here.
Well, I think we have two main goals at CPES, two missions. One is the way I see it, to advance technology, and the way we're doing that right now is through the use of wide bandgap semiconductors and really squeezing everything they have in them to advance the performance that they can enable us to achieve. Second objective we have is the formation of workforce of the future, our grad students. That's our main product, I think. That's why we have a strong collaboration with industry, because they are here for that. In the end, they are the ones recruiting our students, and they appreciate them because of the way in which we conduct this work, which is hands-on, very experimentally oriented.
Something unique about CPES is that it's quite vertically integrated. We have faculty and students with expertise ranging from components such as the semiconductor devices, magnetics, to the materials, also the packaging and integration, the converters, modeling and control, and the system integration and even power system level analysis. By having those varying levels of expertise, we're able to kind of pool our knowledge to create components and technologies, methodologies that will benefit the systems as a whole rather than optimizing each as an individual.
The research work we are doing is not only about the theory or simulation. We have to build hardware to prove whatever the concept we propose. So all the CPES students, before they graduate, they need to build some converter. And eventually they even need to destroy this converter to find a limit of this hardware.
That's the essence of engineering, I think. Engineers at the end are producing physical products. All the models and our intellectual processes that we use for creativity are not sufficient. So because of that, we think it's essential that our graduate students who are actually working at the borderline of the human knowledge still have this relationship that at the end, if they are engineers, it's not just understanding. You have to make a real, useful, physical thing.
Our lab is set up in an open environment. We don't do cubicles. We want to make sure every student has access to all the other students. We do seminars so that we can share knowledge of different projects that are going on. But we do encourage people to move about between different areas, talk about different, gate drivers and different devices that they're using, so that they can really cut down on their time to learn that technology. They can just go ask another student to learn that really quickly.
Every technological advancement that we have or develop in CPES will permeate the whole operation, because it's an open lab and there's a lot of lateral flow of information, and just everyone's picking up on the new work that everyone else is doing.
So having that real world experience while you're just getting educated and doing advanced research we think is very essential for the complete educational engineers.
I think a key motivator for a lot of us at CPES is sustainability. So whether that means electrified transportation or integration of renewable energy and distributed energy generation and storage, that all can have profound impacts on the future of our society.
Our goal is really to achieve net zero carbon emissions. And to achieve that goal, we have to fundamentally transform the electric power grid, the biggest and complex machine built by the humankind. So the electric power grid right now is going through this grand transformation process. People are shifting away from the fossil fuel-based power generation plants to more and more renewable energy resources. So every electrons generated by the renewable energies has to go through the power electronic converters.
So that we can take energy wherever it's available. Is it the solar panel or a wind or a battery or something, wherever it is around the world, move it through the wires at the speed of light and deliver it to whoever needs it, wherever they need it at any time. If we can do that, then we will not need to have stationary big nuclear power plants, big hydropower, big burners of oil and gas. We will still have a huge network, but it will be an electronic network, and we could save our planet from all the bad things that we have been doing to it in the last 20 years.
To me, the CPES consortium is really the life that sustains us. Without the consortium, we don't have the lab, we don't have half of the operations really. So it's really what keeps us alive. And it's also meant or aimed at developing the really fundamental technology challenges that we have that we can then apply to specific sponsored projects from industry and from government that are all building on top of the research we do within the consortia. So it's really a perfect model to have.
One of the faculty in CPES said recently that CPES Industrial Consortia represent open and collaborative forum, which is indeed the right word to use, where industry and CPES researchers explore new power electronic solutions for more efficient energy delivery, for more efficient power conversion, and obviously cheaper power electronic technologies.
Fred Lee, who founded this, was a master artist in developing this mutual trust between industry and the dreamers and researchers, and we are now riding on that wave that he developed and enjoying it, I think, on both sides.
One of the current research under the PMC is to develop this like a low voltage and the gallium nitride power devices, potentially for the consumer electronics application, for example, the mobile phones and some of the like the VR system, etc. And those are like research basically are entirely motivated by the industrial needs.
So in CPES, we have right now 3 mini consortium. So the Power Management Consortium, High Density Integration Consortium, and the High Power Converter System Consortium. And all these 3 consortium basically were working together to tackle this big problem, the energy problem, but also each of them has its unique focus.
I think the 3 consortia cover very accurately the breadth of the research that we do at CPES, which right now basically covering every aspect of power electronics, perhaps not motor drives, but from the power conversion standpoint, we're really covering every aspect from devices, components, semiconductors, packaging integration, EMI, modeling, power conversion, the impact of power topology in the system, all the way up to the grid. So it's very comprehensive.
So today in the PMC, we are working on many these high-frequency converter. So for example, like a 48 to 1 volt converter for data center, or 400 volt to 12 volt converter for telecom system. So with this advanced gallium nitride power semiconductor, so we are able to do something we never can do in before with silicon. And we can push the switch frequency of the power converter much higher than today's design. So for example, today's converter with silicon only running at 100 kHz. But with the gallium nitride device, we could push frequency to 1 MHz, 10 times higher. So we can significantly increase switch frequency, but also we will run this converter with self-switching capability. And also we will integrate this transformer inductor with the PCB winding. And then eventually, we will also use this advanced control to control these different converters to make sure we can have very high efficient and very reliable system for the future data center and the computer system.
We are working on 3 aspects. The first one is efficiency, second one is power density, third one is the cost. We pushing for very high efficiency is 1.5 higher than the state of the art, which could save almost 50% of the consumed energy. And in terms of the size, this one has to fit in the car, so we have to push for very high density. So we're pushing for high switching frequency, around 500 kilohertz, so we can achieve smaller size, which is 5 times smaller compared to the other product. And in terms of the cost, we are working on a fully automated solution. So all the magnetics, the wirings are embedded into the PCB, so we can eliminate all the labor-intensive work and has a significant reduction in the cost.
My project is high efficiency, high power density, 48 volt to 1 volt converters for data centers. In this solution, it consists of a LLC resonant converter as first stage and the multi-phase buck as a second stage. And for the second solution, we call it a Sigma converter. These 2 converters is connected in a quasi-parallel structure. From the input side, these 2 converters is in series, and from the output side, these 2 converters is in parallel. And finally, this solution can be much more can achieve higher efficiency and power density.
HDI is really unique in that it brings together a wide variety of students and faculty with a wide variety of expertise that are all complementary to each other.
It will not be possible to come up with magnetic materials, what we did, without the consortium money. It will not be possible for us to develop this coating materials without consortium funding. It will not be possible for us to come up with nano-silver die attaching material without the consortium money. So all that stuff, I think, is this is why, and I love the working with CPES and for this many years, and is because of this the freedom, the flexibility of looking at more fundamental issues that will make a fundamental contribution to power electronics.
So we're working on a project for the Office of Naval Research called an Integrated Power Electronics Building Block. And the PEB concept, Power Electronics Building Block, is not new, but what we're trying to do is create a new spin on that by enabling higher levels of integration through power electronics packaging. Essentially, we're trying to achieve 5 times higher power density and lighter weight by using advanced power electronics packaging techniques. And so essentially we're bringing the whole converter components into the package level in order to get those higher levels of integration, which could then serve as the foundation for building up the electrical power systems of more electric ships.
In our HDI project, we studied the wide bandgap power devices reliability based on the real application scenario. So basically, this means that we extract the factors that could stress the device in real application, and we studied how these factors could impact the device and potentially degrade or fail the device. We studied how the devices will fail, and potentially we can give some improvements on the device design and on the circuit design.
By fabricating prototypes in our packaging lab, we are able to investigate advanced wide bandgap devices with a level of real-world fidelity that can't be replicated through simulation alone. In our labs, we've performed thermal analysis on sintered silver bonds that enable the packaging of 10 kilovolt silicon carbide power devices.
Emerging substrate technologies allows for the design of high-density power converters with improved manufacturability and scalability. Only by prototyping these power modules are we able to fully understand the electrical and thermal trade-offs for a 250 kilowatt power converter.
Embedding semiconductor devices in a PCB, such as the devices in this half-bridge module here, can greatly improve the efficiency, size, and cost of the converters that they're implemented into. This is of particular importance in applications such as electric vehicles, where cost, size, and weight are of the utmost importance.
And then HPCS, the High Power Conversion System Consortium, is looking at the not just the larger high power converter systems and converters themselves, but really looking at the impact that power electronics has on these systems, whether it is a distribution system in a car or on board a ship, or the grid now, from distribution to transmission level. This is the type of work we're doing right now.
This is a 200 kilowatts power hardware in the loop testbed. What it allows us to do is that we can bring the hardware that we're developing in this lab and physically connect it and test it while emulating a large system like a microgrid.
Instead of doing conducting optimization of 1 or 2 converters, we're actually focusing on optimization solutions that solve system-level design challenges, including the design interactions from different technology fields and the different design levels. So from our research, we should offer some answers on how to design the modular power electronic system to be lighter, smaller, and more efficient.
I think our mission, basically, generally speaking, university research mission is try to explore new territory, new frontiers, and try to pave the road for industry.